So what we're going to look at is redox. Redox is part of chemistry. It's you'll probably remember it a little bit from GCSE. It was, you might have heard of, or you might be able to remember actually from GCSE when you've come across the term oil rig. And sometimes we write it downwards, upwards. It all sort of goes all over the shop. That oil rig, so oxidation is loss, and then oil rig, so rig being reduction, is gain. Oops, is gain. This is all in terms of losing and gaining electrons in a chemical reaction. It relates to displacement reactions, and we're just going to basically go back sort of to basics with it and then build up into a bit more detail about where it gets to when we do it at A level. So basically, yeah, that's what we're going to start off with, is looking at redox reactions, just looking at just oxidation and reduction, and what we're going with there. So it's basically start of a recap and then getting a bit more into like the next levels of what happens with redox at A level. I'm just going to try and move this bar. There we go. So redox, what we generally look at is we're going to look at what happens in a redox reaction. We're going to learn how to identify oxidizing agents and which ones are reducing agents in a redox reaction. So when we actually see a redox reaction, can we pick out which ones are oxidizing, which ones are reducing? We're going to learn how to construct redox equations from half equations. So actually how to make those half equations, how to put them together to make a redox equation. So basically in a redox equation, we're going to get rid of any spectator molecules that we don't need. I'm actually going to look at working out oxidation numbers as well. We might go on to the next bit of redox as well today if we have time, but I'm not 100% sure. If not, we'll do that on Thursday. So redox. So bit of a recap now. So redox, we've already said, oil rig, oxidation is loss, reduction is gain. So when we talk about this, we say when a substance is oxidized, it loses an electron, but it has gained oxygen. So that is true. So when a substance is oxidized, it gains an oxygen. So then we've got this situation. So when aluminium is extracted from aluminium oxide, so we're removing the aluminium from aluminium oxide, the aluminium ions are oxidized. Well, what we're doing in this situation is we're removing the aluminium from the oxygen. So we're removing that oxidation. So it will be reduction in this situation. So the aluminium ions are not oxidized. So that is false. When a substance loses electrons, it is oxidized, and that is correct. So if you think of oil rig, oxidation is loss. Oxidation is loss of electrons. Reduction is gain of electrons. So when a substance loses electrons, it is oxidized. So that is true. When a substance burns, it is reduced. And this is one that can cause lots of confusion even. But when a substance is burned, it is oxidized because we are burning it in the presence of oxygen. If you think back to the fire triangle at key stage 3, oxygen is one of those key important participants in the fire triangle, and we need oxygen to be there. So we're not reducing it, we're not removing oxygen, we're adding oxygen. So when a substance is burned, it is oxidized. So it's false, it's not reduced. And then finally, the formation of sodium atoms from sodium plus ions is a reduction reaction. So remembering when we have a plus symbol, that means we've got a loss of electrons. So if we've gone from a plus to a neutral, we must have gained an electron. So if we have gained an electron, that means it must be a reduction reaction. So therefore, this is true. The formation of sodium atoms from sodium ions is a reduction reaction. So what are redox reactions? We use the term redox reactions a lot. What does it mean? I've said it a lot. We haven't actually covered it. So a redox reaction is a reaction in which one substance is reduced and another is oxidized. So we're reducing and oxidizing in that one reaction. So that is what a redox reaction is. That's where we get the term. So so some people say redox, which we got reduced. And so the RED, the red from reduced, is the beginning of redox, and ox for oxidized at the end, so redox reaction. So you might have seen thermite before. So thermite reactions, in thermite reaction, which we've got an image of there, we're going to look at which substance is reduced and which is oxidized. So again, I'm going to keep putting oil rig on. I know it's probably going back to really basics, but it's actually really good to just keep reminding ourselves of oil rig. So I'm going to write it on. So obviously oxidation is loss, reduction is gain. So let's have a look here then. We're going from aluminium to aluminium oxide. So actually our aluminium, so this obviously when we're talking about oil rig is in terms of electrons. So don't let that confuse you when I'm saying, oh, we're gaining an oxygen. Yes, we might be gaining oxygen in oxidation, but that's not a loss. It doesn't matter that we're gaining oxygen, even though we're saying oxidation is loss, because the loss is in terms of electrons. So yeah, our aluminium here is going from aluminium to aluminium oxide. So it has gained this oxygen. So aluminium oxide here goes to aluminium. Aluminium goes to aluminium oxide. So that means that is oxidized. And our iron 3 oxide loses its oxygen to become iron, which means that this is reduced. Which, here we go. Oh, can't see it from all my writing. Erase all, there we go. So the iron 3 ions are reduced and the aluminium ions are oxidized. So oxidation and reduction can be used to describe any of these following processes, and these are really good to learn. You can get asked lots of random sort of 1 mark questions about these sorts of points, so they're quite good to remember really. So we'll go through them, and this would maybe be at a later point. Oops, I want to take the pen off. Something good to look at later and maybe write down. So oxidation reduction can be used to describe any of the following process. So any addition of oxygen to a molecule, to a compound, is an oxidation. So if we're adding oxygen to something, that is a form of oxidation. If we lose hydrogen, that is also a form of oxidation. Also, if we lose electrons, that is also a form of oxidation. So we can, oxidation reduction describes any, well, oxidation is any of those 3 possible processes. So either the addition of oxygen, the loss of hydrogen, or the loss of electrons. Reduction, as you can probably guess, is the opposite. But, oh, here's some examples actually, forgot that then. So for example, the addition of oxygen, we've got 2 moles of magnesium plus O2, and it goes to 2 MgO. So we've added the oxygen to the magnesium, so that is a form of oxidation. We also have a loss of hydrogen, so we have CH3OH, and that becomes CH2O plus H2. So once we haven't lost all the hydrogen, we have lost some of the hydrogen, so therefore that is a loss of hydrogen, so it is also an oxidation reaction. And then finally, loss of electrons, we go from aluminium to aluminium 3 plus 3 electrons, so that is in the form of oxidation. Reduction, on the other hand, is the opposite. So loss of oxygen is an example of reduction. Addition of hydrogen is an example of reduction, and gain of electrons is also an example of reduction. So here's some examples. So we've got 2CuO plus carbon goes to 2Cu plus CO2. So that oxygen, so that copper oxide has lost its oxygen and become 2 copper plus CO2. Got the addition of hydrogen. So for example, got C2H4 plus H2 goes to C2H6, so that extra hydrogen's added. And then obviously our gain of electrons. So we've got fluorine 2 plus 2 electrons goes to 2 fluorine minus. So what are oxidizing and reducing agents? So we talk about what reduction is and what oxidation is, but what are oxidizing and reducing agents? So oxidizing agents are something that can oxidize other species. So they can go in and they can oxidize another species. A reducing agent is something that can reduce other species. Oxidizing agents can accept electrons, whilst a reducing agent will then go in and donate the electrons. Oxidizing agents are themselves reduced, and reducing agents are themselves oxidized, which I know is a bit of a strange way to think about it. Basically, the oxidizing agent isn't the species that is becoming oxidized. That is the species that's becoming oxidized is not the oxidizing agent. The oxidizing agent, whatever it is in this situation, comes in and it can oxidize the other species. It can accept electrons, so we can lose electrons, and itself is reduced. So it is going to gain those electrons itself, so therefore, and lose oxygen itself. And lose oxygen itself and gain hydrogen, so therefore it's reduced. Exact opposite for reducing agents. Reducing agents reduce other species, they donate electrons and are themselves oxidized. So for example, we've got 2 sodium chloride plus fluorine, and it goes to 2NaF plus Cl2. So fluorine, let's look at what fluorine's doing in this situation. So fluorine in this situation is actually oxidizing our chlorine ions. It accepts electrons from the chlorine ions and is reduced to F minus and is an oxidizing agent. So in this situation, fluorine is an oxidizing agent. Oops. Did I not do that? Yes, I did. So yeah, so fluorine over here is acting as an oxidizing agent to the chlorine. So it's breaking it up there. So common oxidizing agents and common reducing agents. So these are some that come up quite regularly. These are quite good to learn and be familiar with because they're the sort of typical examples that you'll get on exam questions. So common oxidizing agents that you will start to become familiar with is things such as concentrated sulfuric acid, which is H2SO4. You can probably see why concentrated sulfuric acid is great because it's got the oxygen in there. We've also got potassium manganate, KMNO4. That's potassium manganate 7. And then we've got potassium dichromate, manganese 4 oxide, chlorine, and hydrogen peroxide. So as you can see with lots of these, they've either got oxygen present. Obviously chlorine doesn't, but obviously chlorine is able to accept electrons quite readily. So that is why chlorine is often a common oxidizing agent. Some common reducing agents are hydrogen, which makes sense because if we add hydrogen, oxidation is lost. We can reduce something by adding hydrogen to it. So if we add hydrogen to it, it can become reduced. Also zinc, and that again will be to do with electrons, because in reducing something we are gaining electrons. So the zinc can donate electrons. Carbon, again, be to do with electron donation. Carbon monoxide is to do with electrons, and also the oxygen. Lithium tetrahydroaluminate 3, and then sodium tetrahydroborate 3. So these are quite ones, you don't have to know them off by heart, but they're quite good to know about them because they come up a lot. So we're going to look at spot the agent now. So what is the role of carbon in the following reaction? So in the following reaction, we've got carbon and we've got oxygen, and it goes into CO2. So it goes into carbon dioxide. So what is the job of carbon in this situation? Well, carbon in this situation, it's not going to be an oxidizing agent. It's not adding any oxygen to the situation. It's not changing that. So carbon in the reaction will be a reducing agent in this situation. So carbon is a reducing agent. The carbon reduces the oxygen and is itself oxidized to CO2. So this carbon becomes oxidized to CO2 and it reduces the oxygen so that carbon itself can be oxidized to CO2. So what is the role of sodium in the following reaction? So in sodium, we've got 2 sodium plus chlorine 2 goes to 2 sodium chloride. Okay, so here we are forming we get 2Na plus Cl2 to 2NaCl. So in this situation, our sodium is going to be acting as a reducing agent. I'm going to explain why. Oops, here we go. So the sodium reduces our chlorine over here to chlorine ions and is itself oxidized to Na+, which is how we can have this change over here. So therefore the sodium reduces, so it is a reducing agent. So what is the role of iron 3 oxide in the following reaction? So we've got iron 3 oxide plus 2 aluminium and 2 aluminium oxide plus 2 iron. So iron in this situation is working as an oxidizing agent. The oxygen is removed from the iron 3 oxide, is given to the aluminium. So the aluminium is oxidized by the oxidizing agent, which obviously is iron 3 oxide. So iron 3 oxide oxidizes the aluminium to Al3+ and is itself reduced to iron. What is the role of the sulfate ions in the following reaction? So we go from copper sulfate plus zinc to zinc sulfate plus copper. Well, in this situation, it's neither a reducing agent nor an oxidizing agent because the sulfate ions have no impact in that situation on the reaction. We would talk about them as being spectator ions in this situation, so they have neither. The role of magnesium in following reactions, we've got magnesium and hydrochloric acid going to magnesium chloride and hydrogen. So our magnesium in this situation is going to be a reducing agent. Going to be a reducing agent because it is able to go in and it's going to bond with our chlorine. And so that makes it a reducing agent. So it's a reducing agent because the magnesium reduces the hydrogen ions in HCl to hydrogen and is itself oxidized to Mg2+ in magnesium chloride. And our final question, what is the role of chlorine in the following reaction? So we've got iron chloride and chlorine to iron 3 chloride. So our chlorine in this situation is an oxidizing agent. And the chlorine oxidizes the iron from Fe2+ to Fe3+ and is itself reduced to Cl. So what we're going to do now is we're going to look at half equations and combining them. So redox half equations, why do we have them? What are the points of them? What they're used for? So redox half equations are used to show separately the oxidation and the reduction parts of a redox reaction. So before we were just sort of showing those whole equations. So for example, we've got magnesium and copper sulfate going to magnesium sulfate plus copper. That's great, but actually sometimes we want to show the oxidation and reduction parts separately. So that's what we're going to do in a moment. I'm going to look at writing those half equations and actually combining them together to make a redox equation. So what we will have is we will have one half equation for magnesium and we're going to have one half equation for copper. And this is our half equations for both. Okay, half equations, as you can see here, they always include the electrons. I'm going to talk about how we actually get to this point in a moment. But we're going to have one half equation for copper, one half for magnesium, and we're going to include those electrons. So I'm going to get to how we've got that far in a second. So let's talk this through. These are our half equations. Why are we here? What has happened? So we have got our half equations. Let's go back up here, actually. I want to go back to this one. So we've got magnesium plus copper sulfate going to magnesium sulfate plus copper. So we're going to look at this straight away and we can work out what is reduced and what is oxidized. So in this situation, our magnesium is going to be oxidized and our copper is going to be reduced. So that is how we then get these equations being formed. So we have copper 2 plus 2 electrons will take us to just copper on its own. And then we have magnesium, and that's going to be reduced because obviously we haven't got the electrons here. We're going to lose some electrons from, no, we're not going to lose some electrons, we're going to add the electrons. So sorry, what have I just said? I've just confused myself. So we are reducing our copper up here, which is what I think I said, because we are adding the electrons on so that we get to copper. And our magnesium, I didn't want to unpause that, the magnesium we are oxidizing. So the magnesium becomes magnesium ion plus 2 electrons. So that's our half equations. So the copper 2 plus ions are reduced to copper. So this half equation shows us the ions gaining electrons. So here is our ion copper 2 plus, gaining 2 electrons. Therefore, we get copper. And remember, reduction is gain of electrons. So we have this gain of electrons here. Whereas down at the bottom, our magnesium is oxidized to Mg2 plus ions. So magnesium 2 plus ions plus our 2 electrons. So this is showing that we have lost those electrons. Our atom has lost those electrons during that process. So half equations can actually then be combined to give an overall redox equation. And what happens is, because we have 2 electrons in each side of the equation, we can just cancel them out with using standard maths. So if I get this a little bit larger, here we go. So oops, go back to the beginning. So there are half equations, and then in the middle we've got our full equation. I'm going to get rid of that full equation straight away because we don't need to worry about that now. We want to make a redox equation. We're going to use our 2 half equations to get there. We've got our 2 half equations. We've got the 2 electrons on both sides, so we can cancel those 2 electrons out straight away. When we cancel them out, we get this. We get Cu2 plus, so copper ions, plus magnesium goes to copper plus magnesium ions. And that is our redox equation so far. So sometimes, and this is where it gets interesting, one or both of our half equations have to be multiplied by something to balance our electrons on each side of the arrow. For that one, we didn't need to do that, but we're going to look at a different example now, where we're going to need to multiply them by 2. So for example, we've got iodine ions and 2 electrons goes to 2I. No, we haven't got iodine ions. We've got iodine plus 2 electrons goes to 2 iodine ions. And then we go from iron ions to iron 3 plus an electron. So we've obviously got our reduction at the top and our oxidation at the bottom. Our issue is this isn't balanced. So what we need to do is multiply both sides by 2. So to do that, we would just, oops, went through really quickly, brackets over that whole bottom equation, multiply everything in those brackets by 2. Then we would get 2Fe2 plus goes to 2Fe3 plus 2E. Now our electrons are balanced on both sides of the equation. Then we can then combine them to make it as one whole redox reaction. So then we can cancel out the electrons like we did before, pop that whole equation together. So then we get iodine plus 2 lots of iron ions goes to 2 lots of iodine ions plus 2 lots of iron ions. So you can see that process there happening. Another example, we're going to look at this. So we're going to look at the half equation for reduction of MnO4 minus to Mn2 plus. So what we're going to do is put them on the right side of the equation, right side of the reaction arrow. I'm going to use water molecules to balance the oxygen atoms on both sides of the equation. So let's get this up. So we're going to look at what the half equation is for reduction of goes so fast, MnO4 minus to Mn2 plus. So we're going to put them on the right sides of the equation. We know it's that way around because we've gone from, we're talking about the reduction of this molecule here. So because we're reducing that molecule needs to be on the left, this molecule at the bottom needs to be on the right. So there we go, got that sorted straight away. We know they're on either sides of the equation here. We've already said that we're going to, we've already said here, we're going to use water molecules to balance the oxygen atoms on both sides. So we can do that straight away. Well, we've got 4 oxygens over here, so we want 4 H2O over on this side. And then we're going to have a look at what on earth is going to happen in this big gap over here. So we've got some balancing going on. So we then need to add some hydrogen ions because the conditions are acidic to balance the hydrogen atoms on both sides. So then what happens is, whoops, just come really quickly. Where's our hydrogen? Here we go. We've got our hydrogen over here. So we need to have AH plus on this side so that our hydrogen ions are now balanced. And then we also need to add our electrons to balance the charges on both sides because obviously we've had a reduction. So because of that, because we are, it'll be 5 electrons being added on because of our charge over here. We were already on a minus charge, we'd already got a positive charge, and we've obviously got the 2 plus charge over there. So it's going to add 5 electrons on to get to our 2 plus charge over here. Then our hydrogen ions and our water molecules have to be cancelled out in the resulting equation. So we should then get, oops, I didn't realise I'd left that plain. So we had this. So there are 2 half equations now, but sort of disappeared for a while. So we had 2MnO4 plus 16H plus 10, 2MnO2 plus 8H2O. We can then go in, I feel like I missed a step. Yeah, did I miss a step here? Where are my electrons? Yeah, I did miss making the half equations. I thought that didn't make sense. So now we want to make the half equations from our full equations. So we've got our full equation here. We need to balance out, well, we need to write for 2 half equations. So writing for 2 half equations, we've got this here, but what we need to do is we actually need to balance out our electrons. Well, to balance out our electrons, we need to multiply this one by 5, multiply the top one by 2. So there we go. We can then get rid of both of the electrons because they're both at 10, and we can get this full equation in the middle. Then we can cancel out our water and our hydrogen. So that should then look like this. So we can remove our hydrogen. We can then go, well, cancel them out. So then we've just got 6H on one side. Do the same with water. If it's going to bother doing that. No, I'm not going to bother doing that. Fantastic. So let's have a look at these. We're going to look at how many ions, no, not how many ions, what am I talking about? How many electrons are needed to balance these equations. So if we have got Fe2 plus, and we're going to go to Fe3 plus, plus something, so how many electrons would that be to balance this equation? Well, to balance this equation then, we would need 1 electron there to balance that out. Because obviously, if we've got a positive charge, that means that we have lost an electron. So we've got an extra positive charge, which means we've lost an electron, so it needs to be plus 1 electron. Okay, so here we've got iodine plus a set amount of electrons gives us 2 iodine ions. So for this one, we're going to oxidize the iodine to make it into our ion. But remember, we've got 2 moles here, so it's going to be 2, those numbers aren't even in order, 2 electrons there. So we've got 2 chlorine ions. It's going to go to chlorine plus a certain amount of electrons. Well, this one's nice and clear. So this one's going to, it was 2Cl minus. So to then just go back to here, we want to get rid of 2 electrons. O2 plus a certain amount of electrons to go to 2 O2 minus. Well, for this one, what we want to do, it's going to be 4. So let me talk through why it's going to be 4. So obviously we've got 2 lots of oxygen here, which straight away, if it was just going from O2 to 2O minus, that would be 2. But we've got a double negative charge up at the top, so we've got a 2 minus charge, but we've got 2 lots of oxygen, so that would be 4 electrons. 5, we've got SN4 plus going to SN2 plus, so we're just going to add on 2 electrons because our charge is difference by 2. Magnesium oxide plus ions plus hydrogen plus a set amount of electrons to not magnesium. So we've got a charge of minus here plus, I'm going to 2 plus here. So remember, we've got 4 lots of oxygens here. And we've got our hydrogens here. Over here on our balance side, we've got a 2 plus charge. Okay, so to get that to a 2 plus, we are going to need to remove, or add, sorry, 5 electrons. And then finally, we've got a 2 minus charge here, so we've got 8, 9, 18. So it's going to be 6 for this one. So what we're going to look at now is actually combining those half equations. So can we combine these pairs of half equations? So we've got iodine, 2 electrons goes to 2 iodine ions, and then we've got 2 chlorine ions going to chlorine plus 2 electrons. So like we said before, we cancel out those electrons. We add the I2, our 2Cl minus goes to 2I minus plus Cl2 because we've cancelled out our electrons. And I'm sure that's supposed to not show us them straight away, but never mind, we'll go with it. Again, talking this one through. So we can see better. Combining them again, we're going to cancel out our electrons, but our numbers of electrons aren't the same on both sides. So the minute here, we're going to have to multiply everything on this side by 4. So we'd have 4 Li, 4 and 4 here. So now we can cancel out our electrons on both sides. Put our oxygen in there, our lithium in here, in there, and that there. So that's how it combined again there. Okay, combining this one. This one's a nice simple one again because our electrons are balanced on each side, so we can cancel our electrons out. Everything on the left hand side together, adding them on. Everything on the right hand side together, adding them on. This time, our electrons aren't balanced, so we're going to have to look at that. So we've got 5 electrons and we've got 1 electron, so we're just going to multiply everything in these brackets by 5. Add on our 5s there because, oops, we've multiplied by 5. Cross out our electrons now, and then just do the same. Everything on the left-hand side, so these 2 straight across to there. I'm there going to here, and then everything on our right-hand side, so this. And just add it on over here. It's nice and straightforward. And our last one, oops. We had 4 electrons and 6 electrons. Obviously, we can't cancel them out straight away, so we're going to need to do something to this. So actually, the first number that they both go into is 12, 4 and 6. So we're going to multiply everything in this bracket by 2, and then we're going to multiply everything in this bracket by 3. So then we should have 2. 2, 12, 28, 4, 14. I'll have 3, 3, 3, 12, 12. So straight away, I'm going to get a different pen colour now. We can cancel out our electrons, so we can just get rid of our electrons, so we don't need to include them. We can actually look at the hydrogens, and we can cancel any of the extras out. So we've got 28 and 12. Well, actually, if we take this 12 off the 28, we then get to 16, so we can get rid of those ones as well. So we can put map now becomes 16, so that can go in here. So that's our 16 there. We can just put this straight down to the bottom as well over here. So that's our left-hand side of the top half equation done. Bottom one, let's look at our water actually. Can we do anything with our waters? Yes, we've got 3 waters over here, 14 over there. We can take our 3 off of 14, which will make our 14, 11. Get rid of those ones. So then we're just left to put that at the bottom over here. And our right-hand side, nice and simple now. Put that straight down to the bottom there. 11 H2O straight down, and then that straight down again. What we're going to do now is we're going to look at oxidation. Oops. No. We're going to look at oxidation numbers. So an element on its own always has an oxidation number of 0. So if we're talking about magnesium, its oxidation state is 0, okay? Something that we should be really happy with, but something on its own is 0. So for a simple ion, the oxidation number is the charge of the ion. So for example, calcium 2 plus, its oxidation state is +2. We have some special examples. These have to be learned. So this will be good when you watch it back later. Give this a pause, make sure you've got these jotted down. Because these are really important. So fluorine's oxidation state is -1. Chlorine's oxidation state is -1. Hydrogen's oxidation state is +1. And oxygen's oxidation state is -2. So in a compound, the sum of the oxidation states is 0. In water, the oxidation numbers of 2 hydrogen atoms and 1 oxygen atom adds up to 0. So as we said before, hydrogen has an oxidation state of +1. So 2 lots of +1 would give us 2. Oxygen has an oxidation state of -2. So 2 plus -2 equals 0. So in a compound, the sum of our oxidation states should always be 0. So the sum of the oxidation numbers equals the charge on a complex ion. So this is the important bit. So in SO4 2-, the oxidation numbers add up to -2. So the oxidation number of sulfur can therefore be calculated. And so we just use a bit of algebra like we've got here. So we know, so we use sulfur as X. So we've got 4 lots of -2 because we know the oxidation number of oxygen is -2. We've got 4 lots of -2. And so this overall would equal -2. So we know 4 lots of -2 would equal 2, 4, 6, 8 minus 8. So if we rearrange this equation, pop the pen in. So now we've got 4 lots of -2 equals -8. We've got -8 plus x equals -2. So basically we're working out what x is. So to get there would obviously be +6. So oxidation numbers, the oxidation number of the atom tells you its relative state of oxidation compared to an element on its own, because an element on its own always has an oxidation state of 0, like we said. Again, there is some exceptions to the special examples in Rule 3. So for example, hydrogen in metal hydrides. So the hydrogen in metal hydrides, the hydrogen has an oxidation state of -1 in NaH. It has a high oxidation state of -1, where it would normally have a oxidation state of +1. Oxygen in peroxides. Now, oxygen in peroxide, so for example, a H2O2, oxygen would normally have a oxidation state of -2. In peroxides, oxygen has a oxidation state of +1. And then we also have oxygen in compounds with fluorine. And because fluorine is more electronegative than oxygen, oxygen has an oxidation state of +2. And obviously, like we said before, it would normally be -2. And finally, chlorine in compounds with fluorine or oxygen, because fluorine and oxygen are more electronegative than chlorine. Chlorine can take on several different oxidation states in these compounds, so it's not an actual set one, but it doesn't stick to necessarily the rule that we said. Where was our rule? Here we go, number 3, where we said, chlorine's always -1. Well, actually, when chlorine's with fluorine or oxygen, it could be lots of different things, unfortunately. And that's just because of electronegativity working there. So let's have a go at working out some oxidation numbers. So let's have a look at oxygen. So let's start with oxygen. That's quite a nice one to start with. We've got 2- there. Well, it's quite a simple ion. There's nothing complex here. So we can just go and pop that there straight away. So we want to know what the oxidation number state is of carbon in this one with O2. So obviously it needs to add up to 0. Oxygen isn't going to have anything special going on. It's going to just be its normal -2. So in this situation, we've got 2 lots of oxygen, so it'd be -4. So our carbon in this situation would be +4. We've got chlorine over here, chlorine 2. Now we've got 2 lots of chlorine. Oxidation state of chlorine, well, if it was an ion, chlorine normally is -1. But obviously, we've just got our whole atom there. It's a compound, so that should be 0. Let's have a look at our iron in Fe2O3. So we've got 3 lots of oxygen, which means we've got 2, 4, 6, a -6 charge, which means our iron has to be a +6 charge. We've got a sulfur in H2SO4. Right, so, and we've got our potassium, no, it's not potassium, potassium is a K. We've got our phosphorus in O4-3-, so we can have a look at that one as well. If we've got a 3- charge on the end, that means that's related to our O4, that means it has a +3. This will be our +5, and I'll explain why this is our +5. So obviously hydrogen is a +1 charge. We've got 2 lots of hydrogen. Our oxygen would be 2, 4, 6, 8, -8. So our sulfur will be +5 in that situation. So we're going to look at changes in oxidation number. Just checking the time. Cool. Okay, so oxidation numbers can be used to define the process of oxidation and reduction. During oxidation, our oxidation number increases. Okay, because we lose electrons, our oxidation number increases. So we go from H2, which is our whole compound, which has an oxidation number of 0. And it will increase by 1 because the oxidation number becomes a +1 here because of oxidation occurring. It's happened once, it goes to +1. During reduction, as you can probably guess, the oxidation number decreases because we are doing the exact opposite. So oxidation numbers in names. Oxidation numbers can be used in the names of compounds to indicate which oxidation state a particular element in the compound is in. So the oxidation state is usually put in brackets. So like often when we say iron free and stuff, in Roman numerals after the name. So we've got some examples. So iron 2 hydroxide, which would be FeOH2. So our iron is in oxidation state +2. Iron 3 hydroxide, and our iron is in oxidation state +3. So we'll find a little bit on this before we will start on the next little bit of oxidation and reduction or redox. Is oxygen oxidized or reduced in the following equation? Reaction even. So we've got 4 lithium plus oxygen. Well, can we oxidize oxygen? No, oxygen can be an oxidizing agent, but because it's an oxidizing agent, it itself would be reduced. So the oxidation state of oxygen decreases from 0 to -2. So in this one, we've got iron 3. Is the iron 3 oxidized or reduced in the following reaction? Well, we go from iron 3. It loses its oxygen, which means it is reduced. So an oxidation state for our iron goes from +3 to 0. As we can see here, that's iron 3, and here is at 0. Is the chlorine ion oxidized or reduced in following reaction? So we go from 2Cl- just to Cl2. So actually our oxidation number has decreased. So it has reduced. Oh, sorry, no, it hasn't. It's oxidized. 1 second, so 2Cl. Oh, it goes from -1 to 0, so it's increased because I did my numbers backwards. Sorry. Is zinc oxidized or reduced in the following reaction? So we're going from Zn plus CuSO4 to Cu plus ZnSO4. Well, we've gained the oxygen, so we've had it oxidized, and our oxidation number is going to increase because we'll go from 0 over there to +2. Manganese in manganese oxide. Is it oxidized or reduced? So over here we've got 4-, we're going to 2+. We've lost our oxygen, so we're going to go with reduced. This goes from +7 to +2. And then finally, chromium. Is it oxidized or reduced in the following reaction? Where is our chromium? That is reduced because we've lost oxygen. Okay, so what I'm just going to quickly do is try and close this. Nice. And just start, or attempt to start, if I can get it to actually do what I want it to do, just the next little bit here, which is redox reactions part 2. We'll have a little quick start to this and then finish this on Thursday. So looking into redox reactions in more detail. So we're going to understand redox reactions in more detail, learn about the reactions of metals with acids, learn about disproportionation, and learn about extracting metals. So we're going to have a look at displacement reactions. Displacement reactions you probably can remember from all the way back in year 7 or 8, in GCSE, and they come back again. So zinc and copper sulfate undergo displacement reaction. And this displacement reaction is actually a redox reaction. So what we're going to do is we're going to find out what this redox reaction is and what's happening. So we've got zinc and copper to sulfate. It's copper to sulfate. So the zinc, as we know from our reactivity series, why is this not working? There we go. Zinc is more reactive than copper. So zinc is going to come in and displace our copper. So we go Zn plus copper sulfate, and we get then zinc sulfate. I'm just writing this down as I go, going to copper. So it forms zinc sulfate and copper. So the equation for this reaction, like we said before, can be split into 2 half equations, one for our oxidation of zinc and one for our reduction of copper. So our oxidation of zinc Oxidation is our loss of electrons. So obviously zinc has gone from 0 and then it has gone to Zn 2 plus 2 electrons. And we know that's happened because of the charge that would be needed. And the bottom one, we've gone from Cu2 plus to 2 electrons goes to Cu, and that is our reduction, our gain of electrons. We can work out this has happened in that way because of our charges over here. So the changes in oxidation state also show that zinc is oxidized and copper is reduced, which is what we've already said. So our oxidation state goes from 0 to +2 in our zinc, and in copper it goes from +2 to 0. The sulfate ions in this situation act as spectator ions in this reaction. So this means that they aren't directly involved in reaction, but they remain unchanged in the solution. So actually when we write that redox reaction and we've got remove those electrons, we can put this back together. Those sulfate ions here, they're unchanged. They stay exactly the same throughout the whole process, so there's no changes there. There are always a 2- charge on both of them, which is why we had that 2+ charge before. So let's have a look at these then. We need to decide if what is being oxidized, what's being reduced, and which one's a spectator ion. So what is being oxidized in this equation? Well, in this equation, magnesium is being oxidized, zinc is being reduced, and nitrogen is part of a spectator ion. This time, what is being oxidized, what is being reduced, and what is a spectator ion? So straight away we can say our spectator ions are the calcium. So we can calcium, what am I doing? Chlorine. So we can sort that one out. Then we can say our calcium is being oxidized because the oxidation number is increasing. So therefore our iron is being reduced. What are our spectator ions again in this one? Okay, so part of our is part of our spectator ion. That is not going to be silver. It is going to be oxygen as part of it. Okay, so what is being oxidized? Well, what's being oxidized is lead. And what is being reduced? Well, that will then be silver. Spectator ions again in this one is going to be our oxygen. What is being oxidized? That's our aluminium, and our iron is going to be reduced. And then finally, our spectator ions in this one is going to be our sulfur. I mean, be sulfur oxide, but we've just got sulfur there. What is being oxidized? That'll be our magnesium, and what is being reduced? That is copper. So just to finish, just have a quick look at reactions of metals with acids. So the reactions of metals with acids are redox reactions. What is oxidized and what is reduced in these reactions? So the reaction of magnesium with hydrochloric acid. Well, in this reaction, our magnesium is being oxidized and our hydrochloric acid is being reduced. So magnesium is oxidized to Mg2+ ions, our hydrochloric acid. So yeah, so our hydrogen ions being reduced and our chlorine are spectator ions in that situation. We've also got the reaction of calcium with sulfuric acid. Our calcium in this one is being oxidized, and then our hydrogen ions are being reduced in that one. So I'm going to leave that there before going on to disproportionation, which gets a little bit complicated.